Morning, all the participants, those who are present, other side of this video, and I would like to welcome Dr. Sanjay Panda, sir. Currently, he is working as an assistant professor in the Department of CSE, NIT Warangal. Prior to this, he worked as the assistant professor and head of the department in CSE, the Triple ITDM, Kurnool. And also he has worked as an assistant professor in our university, BSS Bulla, in the Department of IT. So he's alumni of this university, completed from the CSC department. He completed a PhD from IIT, that is ISM Dhanbad, and MTech from NIT Raulkela. He received 90 plus awards from IEEE, IE, IST, CSI, NCC, and others, which includes 2 silver medals award for the best graduate and the best postgraduate in CSE, IEEE senior member, and ASEAN distinguished speaker. He has published more than 100 papers in reputed journals and conferences. He is a member of IT computing, cloud computing, fault tolerance, load balancing. He delivered more than 70 invited talks and chaired sessions in many national and international conferences. He acted as reviewers in many reputed journals of IEEE, ACM, Elsevier, Spinger, and many reputed conferences. He also served as a guest editor in many international journals. Over to you, sir.
Thank you very much, Biren Barik, sir. My screen is visible, sir?
Yes, sir, it's visible.
Okay. So, good morning, everyone. Welcome to this lecture. Before we start this lecture, let me thank Professor Devudatta Mishra, who is my teacher, and Dr. Trupti Ranjan Mahapatra, sir, Biren Barik, sir, Devasmita Mishra, madam. So, to organize this workshop and giving me an opportunity to share my experience in the topic in the regression techniques and their implementation. So before we start the lecture, I request all the participants to please download RStudio. We are going to do the implementation in the RStudio. And if you do the hands-on with me, then you may get more knowledge how it is working. You can do in your computer system. So it will take time. First we will go for the theory parts, then we will go for the implementation part. So before we start the implementation part, please install this RStudio. It is 170 MB file. It is a long file, but if you install, then you can do hands-on practice with me. So in today's lecture, this is the agenda for today's lecture. First, we will discuss about various regression techniques. So basically, I want to focus on four regression techniques, namely linear regression. Next is your multiple regression. Next is logistic regression. Then there is Poisson regression. And basically, I will focus on these two regression, that is linear and multiple regression. So what you can expect from my lecture is that we will go for a step-by-step illustration, which we are doing manually, complete manually, without any computer or without any support of any simulation tool. First, we will go for illustration. Second, I will tell you how to implement the same thing using R. Third thing is, we'll see whatever result we got in the illustration and whatever result we are getting R, we'll compare that result. We'll see whether the same result we are getting or not. So these three parts we will cover in the linear regression with respect to linear regression and multiple regression. As there is a limited time, I will not go the illustration part in the logistic regression and Poisson regression. So what we'll do, we'll implement the logistic regression and Poisson regression, okay? And I'll tell you why it is important. And I'll tell you what are the existing data sets are there in the RStudio. Using that data sets, you can see how logistic regression and Poisson regression works. This is the second part. Third part, we will see some statistical examples. Once you found some result, either in the illustration and R, so how to get a meaningful conclusion, whether one variable is dependent on another variable, or one variable is independent of another variable. The relationship between whether the two variables is significant or not significant. So that part we will see in the statistical examples. Then I will tell you about two very popular tests, irrespective of the domain, not limited to CSE domain or electronics, electrical or mechanical or production domain. Any domain where you are comparing your model with others' model. So you have to prove that whatever result you got, that result is significant. For that, we have two statistical tests, that is, we'll discuss in details. If time permit, I will also show you the demo, that how you can evaluate very easily the t-test and analysis of variance ANOVA. Then it is followed by, then we'll discuss a set of references if anybody is interested in the data science, not limited to the manufacturing sector, you can go through the references. So let us start with the first one. The first part is our linear regression. Before going to this one, let us see why we need regression, right? So what I can tell in simple term before going to the internal details, suppose you have the data of humidity, let's say temperature of a particular location. Then what you want to do, using this humidity and temperature and other measures associated with weather, you are going to predict whether there is a rain or not, right? So in this problem, if you see, the regression plays an important role. Similarly, another problem you can see, you have the student's CGPA or SGPA or simply GPA. You have a student's score, exam score, let's say GATE exam score. By looking into these two, you will suggest that whether the student will clear a particular interview or not. So such type of modeling where prediction plays an important role, there you can apply this regression technique. So here you can see the regression analysis is a set of statistical processes for estimating the relationship between dependent variable and one or more independent variable. So there are two variables in each and every regression technique. One is the dependent variable, another is called independent variable. Okay, one is dependent, another is independent. Independent variable, with respect to the regression, it may be one independent variable or it may have more than one independent variable. So if you go for dependent variable is also called as outcome variable. Okay, dependent means you don't have, you want to solve a equation. Okay, the resultant is a dependent one, because you need to put some input, then only you are going to get the output. That's why it is called as dependent variable, because its calculation depends upon others' value. Similarly, on the other hand, you have one or more independent variables, which we call as predictors or sometimes called as predictor variable, covariates and features. With respect to different articles, with respect to different web page and book, they are using these terms. So once you identify which one is a dependent variable, which one is independent variable, what is your objective? Here your objective is to find the line, okay, or you can say a more complex linear combination that most closely fits the data according to some mathematical expression. For example, let us see, this is our x-axis, you have some data, okay, this is y-axis, this is x is a variable, y is a variable, forget about the dependent and independent variable, you have set of points like this. So you have to draw a line such that it closely fit all the data, means you can minimize the error with respect to a particular line. Suppose I am drawing a line, okay, then I will see how much these data are close to this particular line, right? So basically our objective in the linear regression is to draw such a line. So we'll see in the form of R also how it works. Now, come to the linear regression. In linear regression, what we are doing, we are using a equation, mathematical equation that is called as y is equal to ax plus b. Very simple equation, y is equal to ax plus b. And later in other regression, we will generalize it. Like here, we are using one variable is our dependent variable, that you can see y is our dependent variable or called as your response variable. Why it is called dependent variable? Because by using the variables x and other coefficient, you can calculate what is the value of y. Otherwise, it is not possible to calculate the variable of y. That's why we call it a dependent variable, or sometimes we also call it a response variable, right? And you can see here another variable is there, x. X is our independent variable, or it is called as a predictor variable. The reason of calling is predictor variable is that by using this you can make a prediction. Without this you cannot make a prediction. Okay, and we are using two constants. One is a, another is b. We'll see more details about this constant while we'll go for r. A and B are the constant, which are called as the coefficient, right? So what we want here, we want to establish a relationship between two variable. One is x, another is y, where x is a independent variable, y is a dependent variable. So whether you go for the data science or machine learning or artificial intelligence, you need some data, some earlier data or past experience data in order to perform a particular thing, right? Like if I have the data of humidity and temperature and other parameters that are associated with weather forecasting, then only I can say whether there is a rain in a particular area or not. Now, what is the problem? Let us see one problem, numerical problem, very step-by-step process will go, linear regression. Try to understand this particular problem. It is saying last year, 5 randomly selected students took a math aptitude test. Okay, so there is a test with respect to mathematics, which we call as a math aptitude test, right? And you have 5 students, 1, 2, 3, 4, 5. Okay, I have taken a small data set to illustrate you, but real life data set, whenever you will do, whether it is a manufacturing work or it may be any other domain, that real life data are very huge. Like in our real scenario, if you see, our student strength is around 6,000, right? So let us understand with 5, then you can simulate very easily with the R, irrespective of the size of the data set. So we got the results of 5 randomly selected students, and that data set consists of two things. One is math aptitude test and the statistics test. Okay, so before the student is going to register for a particular course, let's say that course name is statistics. Okay, so before they want to opt this particular course, we have the data of math aptitude test. Okay, so with respect to this data, statistics department is asking 3 questions which we want to solve using linear regression. The first question, what linear regression equation best predict statistics performance based upon the math aptitude scores? So you have math score, you have also past data. If you see, you have math scores as well as the statistics scores, but your objective is to determine the performance of the statistics score of a particular student using this traditional data, using this, you can say, already means whatever data it is already available. Okay, is it possible to create a linear regression equation which can establish the relationship between math and statistics aptitude course? Okay, score. Second question it is saying, suppose these 5 student data I have the data, their math aptitude score as well as I have the score of statistics course score, right? But I am predicting for a sixth student whose mathematics score is 80. He secured 80 in the math aptitude test. I am asking, what is your expectation? What is your prediction for the student 6 in the statistics test? Okay. So once you create a linear equation, what you can do by using that equation, if you know the score in the math aptitude test, then you can predict the score in the statistics test. That is the second question. Third question is that how well does the regression equation fit the data? Sometimes what happens, the data is noisy. Noisy means whenever you are taking reading from an instrument, the instrument may cause error. Or due to environment, you are getting an error where the range of the value, what you are expecting, the result is beyond that particular range. If such a scenario happen, then how well does the regression equation fit the data? That is the three questions asked by the statistics department, which we are going to solve. Okay. Now, let us see. Here I have taken two variables, xi and yi. Already I mentioned y is equal to ax plus b, right? Where x is our independent variable, right? And y is our dependent variable. So x represent our scores in the math aptitude test. Y is nothing but the scores in the statistics grade, right? Or statistics course grade, right? And I told you we have the data of 5 students. We have the data of 5 students. With this, what we want to calculate? First, we want to create a linear regression equation, right? So the very first step, what you can do here, you can solve this equation. If you solve this equation, if you can get the value of a and b, and you know the input variable is x, okay, that is your independent variable. If I put the variable value in the x, then automatically I will get the value of y. So the very first step is to get the coefficient, that is a and b. The second step is you have given with the x value, okay, so that you can calculate the third thing, that is your y, right? So first step is you will determine ab, next you will determine x, then you will get your dependent variables value, that is y. Okay. So for this, what you need to calculate x bar. So suppose if I say y is equal to ax plus b, then you can say let us determine the value of b. If I want to determine the value of b is nothing but y minus ax, right? But whenever you are calculating, here you have a group of values. Here you have a set of values, right? As there is a set of values are there, so I can take, this is nothing but y bar minus ax bar, right? Here we are not dealing with a single value. We are dealing with a 5 students. As we are dealing with 5 students, what we need to calculate? In order to calculate the value of b, you have to see y bar minus ax bar. So for this, y bar means what? Y bar is nothing but the mean of all the values of y, that is the average value. X is what? X is nothing but the mean value of all the x element. That's why what we are doing here, we are adding these values, that is 95 plus 85 plus 80 plus 70 plus 60, which is equal to 390, right? Similarly, you can add 85, 95, 70, 65 and 70, which is yi, okay, that is 385, and this is divided by 5. In order to get the mean, what you are doing, you are finding the mean. Mean is nothing but the sum of all values divided by the total count. The total count is 5. That is the reason why I have calculated the mean. That is nothing but this is value is called as your x bar. X bar is your 78 and y bar is nothing but your 77. Right? So these two values you require. Now what you require? Now you have to see how each and every individual value is deviating from its mean. Like mean of the value x is 78, mean of y is 77. So we'll see how the individual values are deviating from the mean. What is the reason why we are checking this one? The main reason is that we want to draw a line. So we want all the data points that should be close to this particular line, right? So that you can estimate the value with by minimizing the errors. So if you calculate this xi minus x bar, xi is nothing but the individual value, that is 95, minus x bar we have calculated as 78, which results 17. Similarly, you can calculate 85 minus 78 is 7. Okay, 80 minus 78 is 2, right? 70 minus 78 is minus 8. 60 minus 78 is minus 18. Similarly, you can calculate 85 minus 77 for y. You can calculate 85 minus 77 is 8. 95 minus 77 is 18. 70 minus 77 is minus 7. 65 minus 77 is minus 12. 70 minus 77 is minus 7. Okay. Now, once you determine these values, you also need to determine xi minus x bar square. In the previous slide, you have calculated xi minus x bar. Now, what you are doing, you are just finding its square. That is nothing but 17 into 17, 7 into 7, 2 into 2, minus 8 into minus 8. If you do like this, then you will get this column. Similarly, what we are doing, we are calculating 8 into 8 in order to determine yi minus y bar square. 18 into 18, minus 7 into minus 7, minus 12 into minus 12, and minus 7 into minus 7. So you will get xi minus x bar square and yi minus y bar square. Once you determine this thing, another value you have to determine for linear regression, that is xi minus x bar multiplied by yi minus y bar, which we have calculated here. The multiplication of these two values, 17 into 8, 7 into 18, 2 into minus 7, minus 8 into minus 12, and minus 18 into minus 7. So if you do like this, then you will get this particular column, and I am determining sum of these values, right? So these are the values you have to pre-compute in order to evaluate a particular equation and in order to analyze various performance measures with respect to linear regression. Your objective is not to create a simple equation. Your objective is to check whether all other measures like their standard error, or you can say residuals, whether they are these values also you have to determine in order to decide whether the dependent variable and independent variables are related to each other or not. Now, what you can do, you know the equation is nothing but y is equal to ax plus b. So I told you, in order to find the solution of this particular equation, what you can take, you take b is equal to y minus ax. Or in the first step, I told you that you can take the variable, if you find the value of a and b, you know the value of x, then you can determine the value of y, right? Now, in order to calculate the first coefficient, that is a, in linear regression, we have this formula, that is summation over xi minus x bar, okay, yi minus y bar, divided by summation over xi minus x whole square. Okay, so this value we have already determined. If you check here, this value we have already determined. We have calculated xi minus x bar, yi minus y bar, and if I sum these values, the sum is coming as 470. Okay, so I am writing here 470. Similarly, here what I can do, xi minus x whole square and their sum, xi minus x square you have calculated here, and sum of all xi minus x square for these 5 students is 730. So this value I am putting here. So I am getting the value of a is 0.6438. Okay, now we determine the value a here. So we need another calculation for determining the value b. Then we can easily solve the equation, that is y is equal to ax plus b. Okay, so first regression coefficient is done and the value is 0.6438. Now, once we know this regression coefficient A, you can easily calculate the coefficient B, that is we call as regression slope. So I told you B is equal to nothing but y bar minus A into x bar. If you are going for individual one, then it is y minus A into x, where you are dealing with a single student. But as you are dealing with 5 students, you can say B is equal to y bar minus A into x bar. So you know the value of A in the previous slide. We determined the value of A is your 0.6438, right? And y bar x bar we have calculated. If you remember, let us go to that slide. Yes, y bar is determined as 77, x bar is determined as 78. So that value I am putting here, which results the value of B is 24.767808. So there are 3 questions asked by statistics department, right? The first question they asked, what is the linear regression equation? Second one, they asked, if a student secure 80 in the mathematics test, what is the score I can expect in the statistics course? Third one is nothing but, once you determine the data, how you will know that the data is fit to your model, right? These are the 3 questions. The answer of the first questions, you can say y is equal to ax plus b, right? Y is equal to ax plus b, where a we have calculated as 0.6438. So I am putting 0.6438 here, right? The value of a I am putting here 0.6438, and b value is 26.7808. So the equation is y is equal to 0.6438x plus 26.7808. How you determine this value? It is based upon the scores whatever we have with respect to the 5 students, right? One is with their statistics subject course grade as well as mathematics subject grade. Both we have. Okay, then we calculated these values, right? So imagine in real life the data is very huge. We are not dealing with 5 students, we are dealing with 6,000 students. If we are dealing with 6,000 students, if we can get the data of 6,000 students and solve using linear regression, so whatever coefficient you will get, that is more or less will give it can predict for 6,000 let's say 1 student or 6,000 2 student 3 student or any particular student you want to analyze, that will be closely fit to the line. Okay, now okay, so in this case let us go to the second question. So first question, I hope it is clear. The equation we want to find, we find the equation using linear regression, that is y is equal to 0.6438x plus 26.7808. Now choose a variable for the independent variable x. Choose the value of independent variable x, because the second question asks the independent variable's value is 80. Okay, that is the 80 is the score that you know in the math aptitude test. Okay, what you have to prove? You have to find the dependent variable's value, that is y, right? So independent variable is nothing but the math aptitude test, dependent variable is nothing but the statistics grade. So if a student made 80 in this aptitude test, so we want to determine the values in the statistics, right? So same equation, whatever we find in that equation, I am going to put the value of independent variable, that is x. So this is the equation you got in the previous slide. I mentioned 0.6438x plus 26.7808. So if I put the x value as 80, then what will happen? It will tell me that we can predict the value as 78.2848 in the statistics test, right? If a student secure 80 in the aptitude test, my prediction is 78.2848. But imagine in real, we observe that the values is 85. right? We observe this is a learning process, right? We may not get the right result. Our prediction is that today there is a rain, but there may not be a rain, right? So this is your exact actual value. Suppose the actual value you know that is 85, but system is predicting 78.2848. So the difference between these two is called as error. The difference between these two is called as error. Okay. Suppose I am giving you a data set in which I want to determine a set of values, like for the student 6, let's say the value is 80, student 7, the value is 75, student 8, the value is, let's say, 65. Okay, in the math aptitude score. I am asking what is the grade of these three students in the statistics. So this is the question mark that I am asking to you, right? So now you have more than one value, more than one students to predict, right? So in that case, what happened? Once you determine the prediction, like here we predicted a 78.2848. Let's say here I am getting the value as 73 point something, 234 something like that, and here I am getting 70.685. Then what I can calculate? I can calculate two error. One is called as mean absolute error. Another is called as root mean square error, right? Which says the deviation from the actual result. The actual result is you have to determine once the exam is over. You can analyze what is the exact score. Like I told you, here the exact actual score is 85. Here the actual score is, let's say, 75. Here the actual score is 80. Right? So the difference between this predicted value and this actual value, by using these two, you can estimate two measures in order to say that whether your algorithm is performing well or whether the process is performing well or not. You have to calculate MAE and RMSE. So in order to calculate MAE, what you have to do? You have to calculate 70, let's say 85 minus 78.2848, right? Plus the next one is 75 minus 73.234, right? Plus the last one is 80. Okay, you can take actual value first or you can take predicted value first, because it is a modulus. It will not give you the negative value 70.685 divided by 3. So whatever error you are getting, that is called as your mean absolute error. But whenever you want to go for root mean square error, RMSE, what you have to do? Instead of taking modulus, you will take square, okay, square of these differences, okay, divided by 3, and they are root over. Okay, and many researchers also suggested RMSE is a better parameter in comparison to the mean absolute error. Okay. So this is the second question. If the score is 80 in the math aptitude test, then we are predicting 78.2848 in the statistics test. Now the third question is that how to know whether this model or this equation fit with this data. One of the solutions suggested here that suppose if you see the data, if you see here the data, that what is the range of the data? The range of the data is the lowest value is 60, okay, highest value is 95, right? The range of the values of x and y is 60 to 95. So what you can say? You can say the prediction value should lie between these only. Okay, suppose I am taking 6,000 students data. In 6,000 student data, the range is 60 to 95. So if you are predicting for 6,001 number of 6,001 student, okay, the student with ID 6001, then the value will come in between the 60 to 95. If it is going beyond that, then we can say there is some problem in the calculation or there is some problem in the model, right? That's why here you can see whatever result you are getting 78.2848, it is in the range of 60 to 95. So we can assume this is not the correct one. We cannot say that it is 100% correct, but we can assume this thing that it is coming in the range means the result is maybe correct. Okay, so when you use a linear regression equation, don't use the values for the independent variable that are outside the range of the values. If you are taking outside of the values, that is called as your extrapolation. It can produce unreasonable estimates. Whatever you are estimating, the estimate may not be the correct one. So in order to avoid that, you have to put a limit. The values are in between 60 to 95. If it is going outside this one, then you can say your model may not fit. So this is all about linear regression in theoretical perspective and our step-by-step process. Let us implement the same thing using R. So R is a tool where you can implement. R is a tool which you can perform these things very easily. Once you know the step-by-step process, then R is very easy, right? Because no need to write the entire code, already some functions are there. So those who have installed R Studio, you can see there is a R Studio in your all program. You please click it, R Studio. So it will take, okay. Okay, so please click on R Studio. Now it is starting. Okay, so this is the console of R Studio. So I want to create a file and write everything into that console. So I am going to file. I want to create a new file. Okay. If you are facing any error, please unmute and tell so that you will follow my this hands-on. So I am clicking R script. Okay. Now a blank R script is created. Okay. I want to save this script in desktop with name linear regression. Let's say linear regression, and the extension is .r. You can see here. You can see here the file name is now linear regression.r, right? So here there is a global environment where you have whatever variables you are using, that is reflected here with their values. So in order to clear everything, you have to write rm within bracket. You have to write list is equal to ls bracket. It will clear everything in your R file. Suppose you executed other programs prior to write this program, then it will clear everything. Right now you can see the environment is empty, right? So that there should not be any conflict. So you can see I have taken two values. One is x value, right? I told you x is our independent value. X values I have taken is 95, 85, 80, 70, and 60, right? And we are writing C. What is the meaning of C here? C is a vector. Okay, C is a vector which consists of 5 values. The 5 values are 95, 85, 80, 70, and 60. And this vector I want to store in a variable x, which is our independent variable. Now we have to calculate y. Y is nothing but C of 85, 95, 70, 65, and 70. So you can take these values. In the previous cases, you can see here 95, 85, 80, 70, and 60. I have created a vector. For creating the vector in R, we are writing C of the set of values, right? And for yi, it is 85, 95, 70, 65, and 70. So I am writing another vector. For declaring the vector, the common syntax is C only. So I am taking another vector, but I am storing in another variable y. Okay. Now you have independent variable and dependent variable, right? Now you want to establish a relationship between these two variables. For this, I am declaring another variable. let's say relation. How you will establish relation? This relation using linear model. There is a predefined function linear model LM, and I want to specify that y is a function of x. Y is our dependent variable. So y should be a function of x. That is y is equal to your ax plus b, right? That's why I am writing lm of y tilde symbol. This is a tilde symbol, right? You can see this tilde symbol is available just before the your numeric key 1, right? So lm y tilde symbol x, right? Then I have stored in the relation. This variable you can take any variable x, y relation, anything you can take. There is no problem, right? Now I want to print this relation. Once you define a particular model, linear model, I want to see that how I can print the relation. So this code I am pasting in the chat box. So those who have written, that is okay. Those who have not written, you can directly copy. Okay. Now, what I have to do, here you can see there is a run button. So I am clicking run button. So you can see here the list is cleared. Then I am clicking the run button. Now x is taken. X is having 5 values, right? Then I have taken y is having another 5 values. Then the relation is established, right? Then the print relation, if you write, you can see here you are getting the x value as well as the intercept value. The coefficients values you are getting. The coefficient value with respect to the x is your independent variable you are getting. So you can note down this value 0.6438 and 26.7808, and you check whatever we have already calculated in the slide. So let us see whether we are getting the same value or not. Here you can see we got the value 0.6438, okay, as A, and the intercept as 26.7808. So you can see the exactly the same value we are getting in R. So no need to calculate everything. Once you done, you are aware how it is calculating, you can directly use R, right? Okay. So any problem? Anyone is facing any problem? Please write in the chat box, or you can unmute and tell. Because once you understood this part, then other part will be more easier. Let us spend more time in linear regression. You are facing any problem? I have pasted the code. R session aborted. Sir, you can start. You can restart again. Rajiv Gupta sir, please restart the R. And I have already pasted the things in the chat box. You can copy. Simply you have to create a file. Okay, give the name and store in somewhere in your computer, and paste this code and run it. Okay, so you can see here. You can follow the slides also. In slide also I have clearly mentioned everything. We have taken this one. LM is a function, that is a linear model function to create the regression model. And here you are establishing the relationship between y and x, okay, and a and b, whatever result you are getting, a is called as your slope, b is called as intercept, which is based upon the value x and values of x and y, and the tilde character is nothing but is modeled as a function. Tilde character represents a function. So this is a mistake here. So this is a tilde character is nothing but is modeled as a function, right? And y is modeled as a additive linear function of x. Y is defined in the form of x. So this part we did using R. Okay. So the syntax of LM is first you have to write the formula, and you can explicitly mention the data as well. Suppose the data is present in a CSV file, that is Microsoft Excel file, or data is present in the text file. So you have to supply the data as well. But here the data is too small, so this parameter is optional, right? So formula is nothing but the relationship between x and y, and data is nothing but in which data you want to apply the linear regression. Now you can, in order to get more details about this linear regression model, you can write print summary. If you type summary, you will get more details relation. Let me run it and show you. So you can see while you are writing print summary relation, what you are getting, it is calling LM formula y is a function of x. You are getting more details about the linear regression. So I'll tell some of the parameters. You can see in each and every parameters you can calculate manually, right? But as the time constant is there, I'll tell you how to calculate residuals, how to calculate the standard error, how to calculate residual standard error, and why it is written as 3 degree of freedom. These things I'll tell you. Rest things, for each and everything there is a formula is there. Simply if you put the formula after these calculations, then you will get the these values. You may get slightly deviated value due to the 3 digits or 4 digits you are taking. So based upon that, we are truncating the other digits. So you may get a value slightly different from the whatever values you are getting in R. Now, okay. So here you can see I have written the step-by-step process. If you have not installed R, you please follow this one. These are the results we are getting, which says that y is equal to 0.6438 of x plus 26.7808, where first value represents your slope, second value represents your intercept. So this is the result we are getting if you are writing print summary relation, what I told you. Then let us see what is minimized residual, how to get the residual values. See here, we have calculated the values, or we have formed this linear regression equation using the values of xi and yi, x bar, y bar, or x bar minus x, y bar minus x, or they are square or they are multiplication, right? Then you got this formula that y is equal to 0.6438 and 2678. So now what I will do, in the machine learning perspective also I am telling you, not only the data science perspective, you want to test once this equation is formed using this data, that is the data of the 5 students, I want to check whether this equation works fine for my existing data or not. For this, what I have to do, I assume that I do not know these values. Once I form the equation, I am assuming that I do not know these values. Means dependent values I do not know. What I know the independent values, right? So these independent values I want to put in this equation. That is nothing but 0.6438. I am putting the x value as 95. I am putting x value as 85. I am putting x value as 80. X value is 70. X value is 60. So I do not know what is the value of y. Y value I know, but for calculation of this equation, I am just neglecting this y value, right? So what value I am getting here? I am getting, this is the value. What I can call this one? This is your prediction. This is your predicted value, right? What is these values? These values are actual values. So what you can do? I told you, like you have calculated mean absolute error or root mean square error. Similarly, here what you can do, you can find the difference between the predicted value and the actual value. So you can see here I have calculated the actual value is 85, but the predicted value is 87. Okay. Similarly, actual value is 95, predicted value is 81. So I am getting these values, which I called as residual, right? And sum of these residuals is always 0. In order to cross check whether you have correctly calculated or not, you can see sum of all the residuals is equal to 0. So you can check the result in R also. Okay, these are the residual values you are getting. You can check both results are more or less same, or there may be a little bit difference. Like we are getting 2.9418, but R is saying you will get 2.945. Okay, like that other values are there. You may get a slight change due to means you are taking 4 digit or 3 digit like that. That's why the values are a little bit deviated. Now this thing is clear, that is residual is clear. Okay, now let us go to this coefficient value, right? So here you can see you have calculated the t value. let me tell you the t value before going to these values, right? You know these two values are calculated previously. That is nothing the value of A and value of B, right? A value we got in 0.6438 and B value you got 26.7808. Then I will tell you how to calculate the standard error later. So once you find the standard error, you can calculate the t value. T value is nothing but the ratio between estimate value and the standard error. That is nothing but 26.7808 divided by 30.5184, that is 0.878. 0.6438 divided by 0.3866, that is 1.665. Right? And these are the p values. I'll tell you more details in the p value later, right? Okay, so now let us see how to get some other values like standard errors in the regression slope. Okay, regression slope is this one, standard error in the regression slope, and how to get the residual standard error. For everything, there is a formula is there. So you can see here, once you find the E is nothing but your residual. What residual is saying? Residual is saying the difference between the actual and the predicted one. Okay. So once you determine E, you can find E square. Okay. Just square of this one, right? Then you can calculate the standard error of the regression slope. For this, we are using this formula, that is summation over E square, that is sum of these values, divided by n by 2. Here the n is nothing but the population. The population is 5. We have taken 5 students. Divided by summation over xi minus x whole square. So this is with respect to this column. You have to take xi minus x whole square. So if you calculate that, you are getting the value as 0.3859. In R, we are getting 0.3866. Similarly, in order to find the residual standard error, you will take the numerator part only. That is summation over E square divided by n by 2 root over. So you are getting 10.4255. Okay. So in this manner, just I will tell this illustration because that many people will confuse how to get these values. For each and every value, there is a formula exists that you can apply. Okay. So these are the steps we are applied. Or this is another problem also. Here you can see the problem is saying we have to design a regression equation in which we want to predict the weight of a person. I want to predict the weight of a person where I know the height of the person. Okay, I know the height of the person, means this is x, your independent variable. I want to predict the weight of a person, that is y, that is our dependent variable. What are the steps we have obtained here? Let us see. Carry out the experiment by gathering the observed values. What are the observed values? We have taken 5 students, or we will take in this case 5 heights, 5 persons' heights. That is our observed values of height and their corresponding weight. And what we want to establish? We want to establish the relationship between height and weight. Right? We are forming this relationship model using the predefined function lm. This function is already there in R, in which the code is already written. No need to worry of the code. Then what you got? After applying the lm function, you got the coefficient and you have formed the mathematical equation. Then you can apply summary to get the details of the relation. Okay, in which you can see the residual, which is the difference between the actual and the predicted one. And finally, using this equation, okay, whatever you have formed here, mathematical equation, you can apply the predict function which is available in the R. So these 4 things we have already discussed. I will tell you how to do the prediction. That is same as the second question. If you remember, the statistics department asked if a student secured 80 in the mathematics test, then how much score he will secure in the statistics test, right? Okay, so I have taken the values of heights. There are 10 values I have taken, I hope. Yes, 10 values I have taken, 10 weights I have taken. So I can form let us form a vector here, right? Let me create another file. I want to create another file, okay, for the second problem. Let me save this file in linear regression 1, okay, dot R is the extension that will automatically come. Let us paste this code here, the same code, whatever I said in the chat box. Now what I will do here, I will write the values. What are the values you have? You have the values 151, 174, 138, 186, 128, 136, 179, 163, 152, and 131. So 10 values are there. And in the weight case, you have 63, okay, 81, 56, 91, 47, 57, 76, 72, 62, and 48. Okay. Now the same things you can do, or if you want to do all the things at a time, you can select and press run. Okay. So now you got these values. You got the coefficient is minus 38.451 for B, and A value is 0.6746. Okay. If you apply this one, you are going to get these values, A and B values. Similarly, if you write print summary relation, you want to print the summary relation, you are going to get this value. You can see here. The same thing is written here also. Let me run the summary relation only. Yes, you got this value. But the interesting thing you can see here, why I discussed the second problem. Here you see, here residual is not represented in the form of values. Let us see the previous one. If you see here, the residual is written as 1, 2, 3, 4, 5 because you have 5 samples, 5 students details. But here, the total details you have, that is with respect to 10 people. As the data is more, it is not possible to show with respect to each and every individual term. That's why it is calculating the 5-point summary. This is called as 5-point summary in the data science, which is nothing but the minimum residual value, maximum residual value, median residual value, and first quartile and third quartile. Right? And like the previous one, you are getting the standard error, residual standard error, multiple R squared, adjust R squared, F statistics, and P value. Another thing you can observe if you compare the previous results with this result, here something is written as star and triple star. Let us understand this meaning. What the star indicate? Triple star indicate this value, okay, this value is less than 0.001. Okay, and triple star indicate. Triple star means the value is less than 0.001. 2 star means the value is less than 0.01, so that because whenever we are calculating this p value, we are more observing these things. That's why it is represented in the form of star, where star indicates the value is less than 0.05, which is the desired value as mentioned in the statistics. Okay, and the p value should be less than 0.05. If you are taking 95% confidence interval, I'll tell you later what is 95% confidence interval. But generally, we are taking the p values is less than 0.05. Then you can say your things are working fine. Otherwise, there is no much significant things are there, right? Okay. So now the only one thing left in the linear regression, we want to make a prediction. For predictions, you have to take 2 parameters. One is the object. The object is nothing but whatever you created in the LM function, and the data. Data means the value is 80, or if you want to predict for multiple student or multiple people's height, and you want to predict their weight, then you can take a file name also if there are more values to predict. So see here, what we are doing here, we are creating a data frame. Okay. So here we are creating a data frame A. Okay. In the data frame, I am mentioning data frame you can take multiple vectors. The simplicity I am telling you, this data frame can take multiple vectors, right? So data frame I am mentioning x is equal to, let's say, 170, right? And I want to find the result. Result is a variable. Okay. Result is a variable. The values of result is nothing but the predict function, which is already there in the R, relation, what you got in regression, and you have to take the input as A and print the results. Okay, so if you run these three lines, you will see if a person's height is 170, its weight should be 76.22. So let me share this code. If you want to run in your computer also, you can run. There is some question. Significance of P and P value in regression. I will come to madam. Smita Parija madam, I will come. Can we do this in Minitab software? Madam, I am not aware of this Minitab software because we are using R, Python like this. I do not know, maybe it is available and maybe a better tool. I do not know. Okay. Please show the output of new XY values one more time. New XY values. New XY value means Puspalata madam. Hey Puspalata madam, can you please tell me what you want to show? You have written new XY values. I don't think there is any new values. We are predicting for one new value of X. Okay, which I mentioned here. I have taken X is equal to 170. Oh, you got the result. Thank you very much. Okay, so you can see the value you are getting here is 76.22869. Okay, so similarly, the same thing, if you want to copy, you can copy and run in the first case also. First case also, if you want to run, you take the X value as 80. We have taken because our math aptitude test is 80. I am pasting the same thing in the chat box also. So you can save this to file, later you can run, right? So if you run this one also, you are getting, okay, if the value is 80, okay, you are getting different things, okay. Let me run all, then I am getting the value is 78.28. So you can see here, in the previous case, we got the value is 78.28, or not. Let us see. Yes, 78.2848, they are getting 28767. Okay. So this is all about the linear regression. I hope you have completed this one. Then you can also form a, you will not draw it graphically. You can take the help of this plot chart and you can create a PNG file or JPG file. Generally, we are creating PNG file in R. So you can create this PNG file and you can specify which color you want to take in order to draw a graph. What is the name of the graph and what x-axis indicates, what y-axis indicates, what is the size of, means you can say the width of the line that you can set. So this is the line you are going to get with respect to the height weight regression. So I'll also share this code so that if you are interested in the later point of time, you can do it, right? So if you write this code, you will get a graph like this, which shows the relationship between x and y. X indicates the weight and y indicates your height, right? You will get this graph. Okay. So if you have any doubt, you can ask about linear regression before moving to the next regression, that is multiple regression. Okay, you keep on posting the questions. So whenever I'll see the chat box, I'll answer. So in multiple regression is an extension of our linear regression. The same formula you can see here, y is equal to ax plus b, right? Here I have taken a as another variable, another constant I have written, that is b1, right? So we are generalizing the linear regression. Linear regression case, we are saying y is equal to b plus ax, something like this, right? Now we are generalizing it. We are writing this is a b0, this is a variable, so I am taking b0. This I am taking as b1 here. Like that, it will continue. It may be anything, any number of variables you can take. So in this case, if you see, how many dependent variables are there? Exactly one dependent variables are there, or the response variable is only one. But if you see independent variable, x1 is an independent variable, x2 is an independent variable, xn is also an independent variable. So that is nothing but we have more than one predictor variables. Okay, and these are the constants, right? These are the coefficients b0, b1, b2, bn. Okay, these are the coefficients. So in order to solve the linear regression, first you have to determine this coefficient. Once you determine the coefficient and you know one value of x, then you can predict the value of y. Right? Let us go through a particular problem. Here the problem is we want to predict the job performance of a mechanics, right? That I represent is by y, which is our dependent variable, based upon two tests. One test is our mechanical aptitude test, we represent by x1. Another is based upon the personality test, that is our x2. So in the multiple regression, the minimum number of variables is 2. So you can also illustrate with 3 variables, 4 variables, and 5 variables. As I am taking 2 variables, what I call this one, that is regression with 2 independent variables. Right? See this one, how it works. So you are given with 2 independent variable. One is your x1. x1 is given, x1 variable is one test result, x2 is another test result, and you have to predict the job performance. And already you have the responses of 5 candidates, right? They are test, you know, right? What you have to predict, you have to first go for a mathematical equation which is representing your multiple regression. Then you can predict a particular thing, right? So here our equation is nothing but y is equal to b0 plus b1 into x1 plus b2 into x2. So if I want to find this b0 is nothing but your y minus b1 into x1 minus b2 into x2. Why I have taken this bar? Because I have 5 candidates. If a single candidate is there, this equation will work. If a multiple candidates are there, you can take the bar, right? And if you know this b0, b1, b2 values, or if you know b1 and b2 values, you can predict b0 values, or you can calculate b0 value using this equation. If you know the other values like x1 bar, x2 bar, and y bar. So b1 is calculated using this particular formula. Okay, b2 is also calculated using this particular formula. Right? This formula looks like same. Only you can see here I have taken x2, here I have taken x1, here I have taken x1, here I have taken x2. Just we are flipping, right? So now what you can do in this case, you can see x1 square. X1 square is nothing but the square of this one. Okay, before going to that, I want to tell you I have used 2 variables here. You can see, don't be confused. One is small x1 and small x2. Another is capital X1, capital X2. This capital X1 and X2 is given to you, but these 2 equations are in the form of small x1 and x2. Small x1 and x2. Okay, so I will tell you how to calculate each and every, how to calculate this small value in terms of the capital value. Okay, then only you can solve the equation b1 and b2. So here you can see, before calculating this one, as these values are depending upon these parameters, right? I am calculating this one. X1 square, you can calculate square of x1. X2 square, that is nothing but the square of your x2. That is 8 into 8 is 64. In x1 case, it is 3 into 3 is 9. Like that you calculate for others. You can multiply x1 with y and represent in this column. Like that x2 into y and represent in this column. X1 and x2 and represent in this column. And the sum of your capital X1 square is 90. Sum of capital X2 square is 148. Summation of X1y is 98.8. Summation over X2 into y is 45.6, and summation of X1 and X2 is 99. Right? Now I'll tell you how to calculate this individual one. So in order to calculate the summation of xi square, it is nothing but the small xi square is nothing but summation over capital Xi square minus summation of xi's whole square divided by n. Note that these 2 terms are not same. These 2 terms are not same. This is the individual values square. That is nothing but these values. Right? Their sum. Their sum is 90. Right? But what is this one? Summation of xi square. You find the sum you find the sum of all x1, that is 20, and you take the square. So you are getting that summation of x1 square is 10, summation of x2 square is 32.8. And the generalized formula is here. As we have two variable, I am taking I is equal to 1 here, I is equal to 2 here. Right? Now, you have another formula, that is summation over xi y is equal to summation over capital Xy minus summation of xi into summation of y by n. Okay, here also I have two variables, that's why I have taken I is equal to 1. Okay, so that you can calculate summation of x1y. I is equal to 2, so you can calculate summation of x2y, which results 17.8 and minus 48. So you can see these values I am taking from here. So I hope whenever you follow this slide, you will get the details. The next one is your summation over xi xj. Okay, and you know that I value is equal to either 1 or 2. So in order to formulate these two x value, I am taking I value first I value as 1, j value as 2. So if you do this, then you will get summation of x1, x2 as 3. Right? So once you determine these things, what you have calculated these values. Summation of x1 square, x2 square, x1y, x2y, summation of x1, x2, which is in terms of capital X1 and X2. Note that these are the small variables. Okay, small x1s, which is represented in the form of capital X1 and X2. Once you determine this thing, you can now easily calculate the B1 value, B2 value. That is nothing but summation of x2 square, you calculated as 32.8. Summation of x1y, you have calculated as 17.8. Summation of x1 into x2, you have calculated as 3. Summation of x2y, you have calculated as minus 48. Divided by summation of x1 square is 10. Summation of y1 x2 square is 32.8 minus summation of x1 into xy is 3, which results 2.28. Similarly, you can calculate for B2. B2 is calculated as minus 1.67. Okay. Now, once you find the values of B1 and B2, here we calculated the values of B1 and B2. If you put the values of B1, B2 in this equation, and you know what is x1 bar, what is x2 bar, and y bar, you can predict, you can calculate the values of B0. Okay. So in this case, you can see the y bar is nothing but y summation of y bar is nothing but summation of y divided by 5, because your sample size is 5. That's why I'm writing here 19.5 divided by 5 minus, you know the value is minus 2.28. Then x1 bar is nothing but 20, that is 20 divided by 5 minus of minus 1.67 into x2. X2 is nothing but 24 divided by 5, which results 2.796. Okay. Now you have the equation y is equal to b0 plus b1 x1 and b2 x2, because we have two independent variables and one dependent variables. So what you can do here, if you put these values, then this is your equation. Now we will see how we can do this thing in R. So let me create a new file. Okay, so let me save that file as multiple regression with two variable. So let me write multiple regression .r. Okay, so what are the values I have taken? I have taken x1 is the first variable. The values is nothing but a vector. That's why I'm writing C of 3, 4, 5, 6, 2, and x2 is C of 8, 5, 7, 3, 1. Then your dependent variable y, what you have observed earlier, C value is your minus 3.7, okay, 3.5, 2.5, 11.5, and 5.7. Now, in order to establish a relation, you know the function name is predefined function is LM, that is linear model. But here, y is represented in the form of x1 and x2. Right? The equation is Y is represented in the form of x1 and x2. That's why we are writing y tilde x1 plus x2. Then I want to print this relation in order to get the coefficients. So let me write print relation, and I also want to print the summary of the relation. Summary of the relation. And before run this file, let me copy one command which I have written for linear regression, that I have to clear all files before starting the multiple regression, right? So let us run it. So now I'm pasting this in the chat box also, you can follow. Okay, Pushpalata madam is saying she's not getting the graph. Okay, madam, we'll see in the at the end of the session, right? You can see this graph will come in the document folder. This graph is coming under your document folder. You can go to your my computer and go to your documents. In documents, you can get a file linear regression.png. You will not get there, man. You will get in the document folder. Please cross check. Otherwise, I'll solve this query at the end. Okay, so you can see here you are getting the coefficients values as 2.80. Let us compare with whatever there in the slide. 2.80 we are getting. Yes, here you are getting 2.796. It is more or less equal. Another value is 2.282. We are getting 2.28. Another value is 1.67. In R, we are getting 1.672. So I'm telling you these details because once you understood the concept, then you can apply these functions, because nowadays all the languages are having function. You need not worry about the calculation, but you should know why we are calculating, what are the things we are calculating before applying a particular model. Right? So this is the regression with two independent variables. If you calculate, yes, we got this one which represents this equation, right? And if you print the summary, you can see I have printed the summary as well. In the summary, you will get the similar things as, okay, just a minute. Okay. You can see the summary, you have residuals, you have coefficients, you have the significant code. I already told you it is less than 0.01, then it is represented in the 3 star, less than 0.01, 2 star, and less than 0.05 in single star. Residual error, multiple squared, F statistics, and p values, adjusted p squared, these values you can get, right? Okay. Now, this is the function we are applying. Suppose you have developed a new problem, or you want to solve a new problem with respect to your domain, in which you have 3 variables. So you can write x1 plus x2 plus x3. So y is modeled in terms of these 3 values, right? Now, in order to show the 3 variable concept, I have taken a data set which is already there in the R, which we call as empty cars data set, right? So this data set consists of various properties, or you can say various features of empty cars. For example, with respect to the car, it is showing the mileage per gallon, which we represent by MPG, cylinder displacement, that is represented by DISP, horsepower is represented by HP, and weight of the car is represented by WT. Apart from these, there are lot many parameters are there in this data set. Just I want to tell you how to deal with more than 2 variables. Already we have seen in the 2 variables. I will give a illustration with 3 variables where I am taking MPG as my dependent variable, and DISP, HP, and WT as my predictor or independent variable. So I want to create a multiple regression. Against this y is nothing but your MPG, x1 is nothing but the displacement, x2 is nothing but horsepower, x3 is nothing but weight of the car. See how we can do? So, okay, now you can create another file, R script, and save this file as, let me save this file with multiple regression 1. Multiple regression 1. Okay, then I'm copying the first command to clear everything. Okay, now I want to take the input of car. So I'm writing input is a variable, you can take any variable, and I'm writing empty cars is the data set, right? In the data set, I am not interested for all feature. I am only interested for the four things. One is MPG, another is your DISP. Okay, I am interested for HP is another feature. Another I am interested for WT. Okay. Now what I will do, I want to print the input, but if you print the input, the data set is very huge, so you will get more things. Okay. So let me select all and run this. So you can get the details of the data set here. You can see lot many car is there, right? Duster is there, Mark is there. So many cars name is there. They are now representing in terms of MPG, DISP, HP, and WT. So this data set you need not download. This data set is already there in the R. But I don't want to see, because if a data set is having 6,000 students, as I mentioned, so it is not possible. So what I can do, I can write head of input. Head of input means it will show only first few values. So you can see it is only showing the first six variables, first six car names, right? So let me paste this in the chat box. Okay. So now you have four variables. One is MPG, another is DISP, HP, and WT, in which the first variable is a dependent variable. Other variables are called as your independent variable, right? So what you will do now? Now you have to apply the multiple regression in order to represent. You can see this data set. If you click here in input, you can get the details of the data set, right? Okay, this is the data set. If you click input, where we have set this all the features. Now what I want to do, I want to create a relation. Let me write relation. We are using this variable name in all other cases. And I want to do LM, linear model, in which I mentioned you compare MPG, or you represent MPG in terms of displacement, and HP in terms of the weight, and I am giving the data as input. Here you can see the input is nothing but so many values are there, that is stored in input. That's why I am requiring the second parameter, which is optional, right? So if you do so, you will get the relation. In order to print the relation, you can write print summary, print relation. So if you print the relation, you will get three things. One is with respect to the displacement, with respect to the coefficient of HP, coefficient of WT, and the intercept 37.105505. Let me share this code in the chat box. Okay. So this is the things what we did. Here I have taken a different variable name, that is model. You can take any variable name. We are printing that one, right? Or if you want to print a single coefficient, you want to know only the coefficient, that is A, the value of A, or the value of B0, what I mentioned, or the value of B1, B2, B3, you can follow this one, right? Or if you want to print all the things at a glance, then you can use print relation, right? Okay. And similarly, you can print also the summary. Okay. If you print the summary also, you can get the details. Okay. And this is the equation, right? Y is equal to A plus X displacement plus X1, plus X displacement into X1, X HP into X2, weight into X3. And once you know these coefficients, you can put the values in the coefficient. If a question is asked like this, the question is asked here, that apply equation for the predicting new values for a car with displacement is given as 221. So you know the displacement, you know the horsepower is 102, okay, that is X2 value, you know the weight is 2.91, you can put the value X3, then you can predict the values of y as 22.7104. Okay. So this is all about the multiple regression. What I told you in linear regression, that predicting things. So if you copy that one and paste in the multiple regression one and mentioning the values of the three things, that is DISP. Okay, that displacement is how much? Displacement is 221. Okay, next is okay, HP is 102. Okay, and the last one is WT is equal to 2.91. Then you can also predict using this particular formula. I hope it will work. Yes. It is saying the value is 22.7104. We got with manual calculation. With R, we are getting 22.65987. Right? So this is all about the multiple regression. Let us heading toward the quick to the next two regression. That will not take much time because we have to follow the timeline. Okay. So they see the difference between the linear regression and logistic regression. So sometimes what happens, a problem is given to you and your level, class level is in terms of yes or no. That is nothing but binary. Binary means the value is either 0 or 1. So your response variable, okay, you can see the response variable is taking only two possible values, that is 0 or 1. Or sometimes this response variable is taking more than two values where the probability may be anything in between 0 and 1. Right? So if you see such scenario, hello, is there any doubt? Okay, in linear regression case, what happens? You are predicting the value y, which can extend the range of 0 and 1. But when you go for the logistic regression, there is a assurance that the predicted value y is within the range of 0 to 1. That's why if you remember, I asked the third question, whether whatever equation you are making, whether it is fitting with your data or not. Right? I told you to take in the range of 60 to 95, right? Why? Because it may happen that your data may be less than 60 or maybe greater than 95. But in order to avoid that, what you can do, you can use the logistic regression, which assures you that the value will become within a particular limit. So this is the basic difference between the linear regression and logistic regression. So logistic regression takes the formula y is equal to 1 by 1 plus e to the power minus of b0 plus b1 x plus b2 x. So this equation we know in the multiple regression, right? So it is taken like this. And in order to implement the logistic regression in R, you can use GLM function. Instead of your LM function, which is used in the linear regression and multiple regression, in the logistic regression case, we are taking GLM. And it is taking three things. One is formula, data, like linear and multiple regression. Another additional parameter is added here, that is family. And this family value is binomial for logistic regression, and this family value is Poisson for Poisson regression. Right? Now let us see. I am taking the same MPCAR data set, right, in which I am interested in four features. That is AM. AM is nothing but the transmission mode is automatic or manual. Like there is if it is automatic, then it is 1. If it is manual, it is 0. That is a binary value. And we want to create a logistic regression using three variables. One is cycle, right? HP, horsepower, and weight, right? And we have taken AM. Here, if you see, this AM is maybe automatic or manual, so it is a binary variable, 0 or 1, but other variables are not binary. So, in order to write the model, so let me create another file. In that, let me say this file is logistic regression, logistic regression, the extension is .r. I want to take the input of, okay, so let me clear all the things by copying that command, that is rm list ls. Okay, so let us take the empty card data set. Okay, but in empty cards data set, I am not interested for all the attributes. I am interested only for few features, like I am interested for AM, which represents automatic and manual, that is the transmission mode, CYL cycle, then HP horsepower and weight. Okay. Okay, yes. Now, what I will do, once you have given input, then I want to form a relation, right? That relation, for relation, this logistic regression, we have to take GLM, in which I am specifying the formula is nothing but AM. AM is your automatic or manual. Again, is represented in the form of cycle plus HP plus WT. Okay, and data you can take as a input, what is there in the input variable, and family I am mentioning as binomial. This is fixed. Binomial is fixed for the logistic regression. You need not worry. So if you run this one, I hope you will get the result. Okay, there is a syntax mistake somewhere where I did the syntax mistake. Okay, let me run one by one. Okay, here some syntax mistake is there. We have taken empty cards, yes, AM, cycle, HP, and weight. Okay. Yes, now it is taking. Then relation, if you see, now I want to print the relation in order to get the coefficient. Okay, so you are getting the coefficient, intercept is 19.708, and cycle coefficient is 0.48760, HP coefficient and WT coefficient. Right? So you can also print the summary in order to get these details using the logistic regression. Okay, the summary is that here you can see. Okay, is there any question? Sir, why this fluctuation happens in output, like 2.7 in one scenario, 2.7 in different scenario? Here we got 2.7. Madam, can you please tell me in which context you are saying why this fluctuation happens in output? Fluctuation happens with respect to, no, there is code, there is no fluctuation, right? Code, there is no fluctuation, man. I am going for one by one regression. That's why you are getting different values, because you are dealing with one variable in one case, you are dealing with two variable and three variable, four variable. That's why you are getting different values. Okay. So now you can see in this case here, if you see the p value is written like this. What it indicates? P value shows whether the result is significant or the result is not significant. So if you see, I told you generally p values we are taking less than 0.05 is acceptable in order to say it is significant. If it is greater than 0.05, it is not significant. So you can see in the first case, that is the intercept case and weight case, you are getting the values are less than 0.05, but these two cases you are getting the values are greater than 0.05. Means the relations what you want to establish in terms of cycle and HP is not significant as per logistic regression. So as a summary, you can say, as the values is more than 0.9, we consider that the result is insignificant in contributing the value of the variable AM. However, if you see WT case, it is significant. If it is significant for all, then it is you can go for a better prediction, right? Now let us go to the last regression, that is the Poisson regression. In the Poisson regression, it involves regression model in which the response variable is in the form of counts, not the fractional numbers. The same formula looks like same formula, but here we have taken log of y. Okay, so here you can take y is nothing but your response variable, which is your dependent variable, and x1, x2, these are variables, are your predicted variables or your independent variables, and rest are constants. Okay, so let us directly go because we have very less time. Okay, so in order to apply the Poisson regression, the formula is almost same as this one. I told you in the family case. In the family case, you are writing binomial in the logistic regression, but Poisson regression case, you will take Poisson. The family is called as Poisson, right? So you can take another data set. Another data set is there, WARP breaks. Let me take the data set in order to implement the Poisson regression. Let me create a new file. Okay, in that new file, let me take everything from here, from the logistic regression. Okay. Okay, the data set name is here. There is some predefined data sets are there. Another data set is WARP breaks, right? Data set is there. Okay, I have taken input the whole data set. I don't want to specify the attribute here, so I have taken the complete data set, right? Then, in order to see the details of the data set, I told you you can print the whole data set, or you can print the first few records, that is head input. Okay, let me run this one to show you. Okay, so you can see it is having three different feature. One is breaks, another is wool, another is tension. Where this wool case, it is either A or B. Tension case, it is low or medium or high. So these are the three variables are possible, and breaks is a count. Okay. So in order to apply these relations, what you can do, you can write breaks. Suppose I want to calculate the breaks in terms of three things. That is okay, in terms of two things here, wool and tension. You can generalize to any number of variables. Okay, data is your input. Data you have taken as input. Yes, input, there is no problem. Here they have taken as raw breaks. That's why they have written. Okay, and family I have to mention Poisson. Okay, so if I run this thing, I hope I will get the result. Print relation. Now I am getting the coefficients, right? That is with respect to the tension M. I told you the tension may be the previous slide I mentioned. The tension may be low or medium or high, which is represented as L, M, and H. So you can see the tension with respect to M, H, and wool is written here, right? So let me save this one. Okay, let me save the code first to you. So if you want to run, you can run. Rajiv Gupta sir is asking what is Z here. Let me see where Z I have written. Maybe in the previous one.
Yeah, in summary, yeah.
Yes. That we are calculating whether the values is greater than a particular value or not. Whenever you go, there is a chart is there, sir. In order to evaluate the p value, there is a chart is there, which is where we are calculating the Z value. That's why it is saying whether it is greater than that value or not. If greater than, that is not significant. The chart also I will tell you where to get. While you are going for confidence interval, you will get this chart. Okay, now you you got the result. That result I have already written in the logistic regression case. So in this case, you tell me in the Poisson equation, you can see here the values is much less than your 0.05 because it is coming minus 16. E to the power minus 16 is a very small values, right? What it indicates is a summary. You can tell here that the p values are less than 0.05. So you can conclude there is a impact of the predictor variables on the response variables, right? But previous case you have seen it is not satisfied in all the cases, but in this case it is satisfied. Okay, so this is all about the 4 regression. I hope you got a little bit idea about this regression techniques, right? Now, before closing this section, we have another 15 minutes. Let us spend more time toward the statistical examples. So I don't want to go through these examples, these theory parts you can read, right? So here first part I want to cover, that is called as analysis of covariance. So why we require this analysis of covariance? Because whenever you are getting a result, you are depending upon the value p value. In order to say that whatever observation you have made, that observation is significant or it is not significant, right? For this, what you can do, you can take a variable, a data set, or a set of values, whatever you have taken in linear, multiple, logistic, or Poisson regression, and you can evaluate whether it is statistically significant or not, right? For this, you have a predefined function in R that is called as AOV, right? Analysis of variance, or you have followed by another function, that analysis of variance, right? The functions are there. These functions you can apply to compare your results. So quickly I'll go to the code. Here you can see I have given input as empty car, right? And I am printing the head. I am getting the initial few records. Now, okay, let us go for the code. Okay, let me save the previous code in Poisson regression. Okay, now I want to create a new file. In that new file, I am saving that file as statistical example, right? Statistics, I'm writing statistics 1, or statistics only. Okay, so here I have taken the empty car data set. Let me take empty car data set. In the empty car data set, I am interested in 3 features. One is AM, another is MPG, another is your HP. Any 3 you can take based upon your problem, right? Then I want to print head if you want to print, and I want to go for. So here I have taken HP as your predictor variable and MPG as a response variable, and I want to see the interaction between AM and HP, right? So here you can see, earlier case you are writing y is represented in the form of x1 plus x2. So I told you y is a function of x1, x2. What is I am changing here? I am writing something like x1 into x2. What it is saying? This tells S plus to include both the main effect of x1 and x2, means individual effect of x1, x2, and the joint effect of x1, x2. So if you require like that, then you can use this star in place of plus, right? So in this case, I want to go for analysis of variance, analysis of covariance, that is, I want to represent in the form of MPG, and I want to see what is the effect of HP with MPG, and I want to see what is the effect of AM with MPG, and the joint effort of HP and AM with MPG. And data is given as input. So now I want to print this relation. Let us run this code. Now you got the variable values, right, with degree of freedom. Degree of freedom is nothing but if you are taking 2 different methods. First method -1, second method -1. For example, x value, x case you are taking 5 samples, y case you are taking 5 samples. Okay, the degree of freedom is nothing but 5 minus 1 multiplied by 5 minus 1, right? So in this case we have taken 2, so it is 2 minus 1 into 2 minus 1. Okay, so it is equal to 1, right? So here you can see whatever result we got. You are getting this result. What is it indicating? It is indicating the joint effort of HP and MP. If you print the summary of the relation, let us see the summary of relation. Okay, let me copy the paste this code in the chat box. Yes, sir, I will conclude very soon, right? Please give me another 5 minutes. Okay. So you can see here, if you are running the print relation, you can see in this case, you are getting the interaction, these values. If you compare, the first value is significant, second value is significant, but the joint one, that is HP and AM, is not significant as the values are greater than 0.05. Right? This is the conclusion. Okay. Similarly, you can take HP with AM. Okay. The function of HP AM, if you are taking, it is showing it is significant. Right? They are individual one. It is significant, but whenever you are taking the combined one, that is not significant. Okay. Similarly, you can compare the two different models. Like you want to propose a model and you want to compare with existing model. So here you can see I have taken one model as MPG with HP and AM, MPG with HP plus AM, and I am comparing this model. While comparing this model, what we are using? We are using ANOVA, ANOVA result 1 with result 2. Two models result I am comparing. If you compare that result, you will see that MPG will depend upon the horsepower. Okay, MPG is depending upon your horsepower. What about AM? AM is not significant. Okay, now sorry, it is depending upon both horsepower and auto and manual. That is AM transmission mode, right? So that kind of analysis you can do by the help of the statistical example. Okay, so the last 5 minutes I'll take before taking the questions also. So there is a very popular test, that is t-test, right? So this t-test, if you want to conduct a t-test while you are designing a model, suppose you have a model 1, you want to compare the performance with model 2. You have the result of model 1, you have the result of model 2, right? So if you want to compare two models, you can go for t-test, right? But if you have multiple models, then what I can say, you can go for another test that is called as analysis of variance, that is ANOVA, right? So it is taking a hypothetical test. The meaning of this hypothetical test is we want to say that the two different populations are statistically different or not. That you are going to analyze. So what I am taking? I am taking the null hypothesis. Null hypothesis, I am taking the mean of two different population is 0. What it indicates? It is not significant. While in alternate hypothesis, I am saying the difference between the mean is not equal to 0, means the result is significant. Okay. So what you can see here, your final objective is to reject this null hypothesis and to accept your alternate hypothesis in order to say that it is significant. So in this process, generally, as per the statistics, we are taking the hypothesized mean difference is 0, alpha is equal to 0.05 because we are considering 95% of confidence interval, right? So you can go to Excel. I am telling you, you can go to Microsoft Excel. Okay, let me write Microsoft Excel. In Microsoft Excel, once you open a Microsoft Excel file, you can see there is a option here. Once you click option, there is a add-ins. In add-ins, there is an analysis toolbox is there, right? Then you can click your Excel add-ins, go, and if you don't have these two packages, you please install it. Once you click OK, it will be installed, right? Once it is installed, in the data, you can get here data analysis. Okay, here the data analysis will not be there if you have not installed it, and now it will be available once installation is over. So once you click the data analysis, here everything is there. So you can see t-test and z-test and analysis of variance, various tests are already there. Only you have to select the data. For example, I want to select the data, I have to select a particular range, then automatically the result will be produced in the Microsoft Excel, right? So let me show you that what is the meaning of this result. Suppose I have compared X with Y. X is a different method, Y is a different method. I have compared. I got one t statistics value, right? I got this t statistics value. So once you get this this value, you will get from this Microsoft Excel. No need to worry. All the values will be there. If you input the data, you will get the output. So what is the conclusion you can make here? If T statistics value is less than your T critical 110 or T statistics value is less than T critical 210, you can see in this case it is true. T statistics is less than T critical 110. T statistics is also less than T critical 210. So here we are failed to reject the null hypothesis. Means the result is not significant. On the other hand, you can see here the T statistics value and T critical 110. If you again compare, again it is T statistics is less than T critical 110. So here also the result is not significant. If the value is coming, this value is T statistics value is greater, then you can say it is significant. And how it can be proved alternatively, it can be easily proved because this P critical 110 and P critical 2 values are greater than your 0.05. So there is no significance between X and Y methods in terms of the T test. Okay, in the reverse one, if it is T statistics is greater than T critical 110 and T statistics is greater than T critical 210, then you can say there is a significance in the result. Similarly, in this case, you can see T statistics value is greater than T critical 110, T statistics value is greater than T critical 10. So this result is statistically significant. If you have multiple algorithms, like here I have taken 4 algorithms. So I have taken the null hypothesis as mu1, mu2, mu3 and mu4. Alternate hypothesis, I assume that one of the mean is at least different. And I have taken the alpha value is equal to 0.05 because we are dealing with 95% confidence interval. So similarly, if you want to produce the result, it will say the relationship between the groups and relationship within the groups. And here also you can see that F value is less than F critical. If F value is less than F critical, we are failed to reject the null hypothesis. The result is not significant. But if you see here, in this case, whatever F value you are getting, this value is greater than your F critical. So what you can assume, we reject the null hypothesis. We are rejecting the null hypothesis. Alternatively, you can see this p value is also much less than your 0.05. That's why in statistics point of view, these results are significant, right? So these are the things I just want to discuss with you. These are the references, and the main conclusion is that we discussed the linear regression, multiple regression, logistic regression, and Poisson regression, and I told you how to check the statistical examples, including the ANOVA and t-test. So this is all from my side. If you have any questions, you can ask.
Okay, any question?
Sir, please repeat the add-on in Excel one more time. Yes. So you can go to Excel, right? Microsoft Excel you can open. You can open a blank workbook. Go to File. Click the click the option at the last. It is available options, right? It may vary with respect to your version of Microsoft Excel, but options should be there. So once you click options, then you go for to add-ins. In add-ins, I want to install this analysis toolbox, which is a add-ins, because initially it is not there. I want to add this package, right? So you can click go. So you have to check these two. As it is already installed, it is showing 2 tick mark, but it will be not there in your Microsoft Excel. Once you click it, you press OK. So it will take a little bit time for installation. Let it be 1 minute, not more than 1 minute, right? Then you can see in the data tab, there is a data analysis is there. So these are the things, that is covariance, correlation, whatever may be covered by other expert members, whatever things they discussed, only you have to select the data. For example, I can write here the X variable and Y variable. Okay, they are values, right? Suppose 2, 5, 7, 8, something like this, and you can select this data set and you can perform the analysis, right? Okay, any other question?
Yes, sir.
Sir, please, sir.
Yeah, as we are running out of time, so
Yes.
I'd like
It is
to
already
conclude
11:30.
here.
Yes.
Yeah,
yes.
11:30. Yeah.
Yes, sir.
Thank
Please.
you very much, sir. On behalf of our organizing team, the Department of Production Engineering, Research Bulla, would like to thank for accepting this invitation in very short amount of time. And thank you very much, sir, for this nice hands-on session on using R on the application of data sciences. Yes. And on behalf of all the participants also. Okay, thank you very much, sir.
Thank you very much, Biren sir. Thank you to all the participants for your patience listening the last 2 hours. I'm sharing some link. I'm sharing my YouTube links. So here you can get some test cases, but in data science you can follow the YouTube videos as well. I'll share the material with Dr. Trupi Ranjan sir. So please collect this material. Okay. Thank you everyone. Thank you to all the participants.
Okay. Thank you.